Is starting. Okay, ma'am, I think we can start now.
Thank you. So we have immense pleasure in welcoming our overseas expert for the next session, Mr. Jibin, Director of Business Development at CIED Group, Limburg, Netherlands. He is deeply involved in driving AI adoption across quality assurance, supply chain, and sustainability workflows, and is associated with Right Origins AI, which is an AI-powered SaaS platform that enables traceability and intelligent ESG compliance. With over a decade of experience in business development and partnership building, he is passionate about fostering sustainable and ethical supply chains through innovative technology solutions. In his current role at CIED Group, he leads business development and strategic partnerships, driving the growth and expansion of Right Origins across global markets. He has a proven track record of building and nurturing strategic alliances with unicorn and sunicorn startups, investors, foundations, and government agencies. Prior to this, Mr. Jibin served as Vice President, Ecosystem Relations at ADIF, where he successfully expanded the membership base from 20 to over 500 within a year. He also worked as Head of Startup Initiatives at ZG Consulting, leading multiple projects and programs for the startup ecosystem. Additionally, he brings entrepreneurial experience as a founder and co-founder of 2 hardware startups in the IoT and sport technology domains, which were accelerated and funded by reputed organizations. He is a professional recognized for startup excellence, a Qualcomm Award winner, and Young Entrepreneur Award recipient, Government of Kerala 2014. He has demonstrated exceptional leadership and innovation. He is also a Startup Village Silicon Valley Initiative winner and a Rajiv Motwani Foundation Fellow, with an international exposure through prestigious competitions such as the University Rover Challenge, USA. We are delighted to have Mr. Jibin with us today and look forward to an insightful session. On behalf of the organizing committee and all attendees, I extend a very warm welcome to Mr. Jibin and now I invite him to kindly take over the session. Sir, please.
Hi, Sarah. Thank you so much for that wonderful introduction. I think we can get started right away.
You can share your slides right now.
Yeah, I'm going to do that. So, second. Is it visible?
Yes, it is visible.
Okay, great. Okay, so I was just going through the introduction, fairly well researched, but maybe I should tone down my LinkedIn profile a bit. Thank you so much for the warm welcome. So today we are going to be, speaking about high performance computing and AI, basically what's powering the scalable intelligence in the era of modern AI. So we'll sort of dive deep into the infrastructure behind modern AI. So before that, maybe I can quickly give a short introduction for myself. My name is Jibin. I've been an entrepreneur. Right now I'm working with this organization called Right Origins. I just quickly taken this opportunity to also introduce the organization. And so we are building AI agents for B2B companies in the food and agri sector, ingredient manufacturers across Europe, North America, and South America. And I am responsible for the business development in Europe and North and South American regions as well. So we work on the application layer of AI mostly, but I'm in the beginning of building out this product, we had try to experiment a little bit on running our own LLMs and everything. It was a fun experiment, super expensive as well. But we'll get to the details later probably. So that's basically me. I usually love to do this experiment before I start any sessions, right? I know this is a sort of a mature audience and a faculty audience, but if you could just go to menti.com and input these numbers, that would be fantastic. We just need to do a short poll, a fun activity before we get started. So if you all could just quickly go to this and maybe, jot down this number there, that would be fantastic. I'll share the other screen as well. Sorry. By the way, this is 100% anonymous, so it doesn't matter who we basically will not be able to know who you are. So if you can just jot down how you're feeling today, and maybe how you're feeling about AI today, that would be great. Yeah, the code is here on the top of the screen. I don't know if you can see that. Okay. It's 5770 1108. Okay. Okay, how honest are we being? I don't know. It's a Saturday afternoon, but I feel like the crowd is different, so you all are really excited for the session. So probably this is a good response. Okay, here is wonderful. Would love to see more responses. Okay, so I see a lot of excitement in the room. Okay, so maybe I'll go to the next slide. If you can tell me, get an understanding about the demographics, right? So, okay, I'm already seeing responses. Great. Okay. I'll just give 30 seconds more so that if you're not able to, or if you are able to, jot in the responses, that'd be great. Okay.
Most of the people here are in the assistant associate professor grade.
Okay.
The thing is that many of them have joined through mobile, so they won't be able to switch in between.
That makes sense. Okay. So I'll move on to the next one. So this is probably the agenda that we'll be talking about, today. We'll go through the why of why is there a need for high performance computing for AI, and then we'll dive a little bit deeper into the hardware setup that is required, and then we'll sort of go through the software layer. What are some of the real world examples and how the future would look like, and we conclude the session. So I think it's going to be probably 60 minutes from now on. If you have any questions, please feel free to write in the chat box. We can take it up later as well. Okay, so again, good evening, everyone. Welcome to this the session. Sorry, am I audible? I'm hearing a bit of echo, so I'm not sure.
You're audible.
Okay. So when we talk about AI today, like ChatGPT or Gemini, we often focus on the software, the algorithm, or the Python code, right? But today, I would like to take you behind the curtain to take a look at the engine that's making all this possible. Like you cannot build a skyscraper with nails and hammer. You need to have specialized equipment. You need to have heavy machinery to do that. So similarly, you cannot build modern Gen AI with a laptop. So you need high performance computing. And today we will explore how we move from simple processors to massive supercomputers to power the intelligence that we see sort of today. So historically, if you think about it, computer science had two separate tribes, or two separate tribes with regards to HPC, or high performance computing, and AI. So the tribe one was high performance computing. These were mainly engineers or physicists or applied scientists. They built supercomputers to solve very specific problems, right? And very hard problems as well. And the examples include fluid dynamics, simulating nuclear explosions, weather prediction, airflow modeling for aircrafts, and simulating car and F1 cars, for example, right? So the main concern was precision here. So they care deeply about the accuracy, the numerical accuracy, stability, and correctness, calculating to the 64th decimal point, right? Because small errors could completely change the scientific results. So you can imagine if something were to go wrong, if you were modeling an aircraft wing, right, or predicting a nuclear explosion, or a nuclear reactor simulation, for example. So these things were deterministic, physics-based, and tightly controlled, right? And then on the other side, there were computer scientists and researchers working on the pattern recognition, right? And learning from data. So their problems were very different. Instead of simulating physics, they were figuring out a cat in a photo, or recognizing a cat in a photo, transcribing speech and things like that, or translating languages. AI did not quite require the perfect math at that point in time. So these systems worked with probabilities and approximations, right? So you could get away with not having that level of precision as well. So if the answer was good enough, that was often sufficient. Now, AI models were tolerant to noise and error as well, and they focus more on scale and data than on exact numerical precision. And for a long time, these two worlds remain largely separate. So we had traditional HPCs on the other side and AI on the other side. They use different algorithms, different hardware, even spoke different technical languages, right? So now the convergence of the convergence happened around 2010, 2012 with deep learning boom. I'm sure a lot of you would remember that time period. As neural networks become deeper and more complex, AI researchers realize that to make their models smarter, they need far more computation than a single machine could provide, right? So at that point, AI sort of turned into HPC and said, hey, you have a lot of compute power. Researchers began to borrow ideas from them. Ideas and hardware and other systems designed for the supercomputing world. Now, massive parallelism, distributed systems, and specialized hardware become essential for the AI or modern AI that we see today. So today, these two tribes have effectively merged, right? So the world's fastest supercomputer are no longer used for physics and engineering, as you would know. They are increasingly built and optimized for AI workloads. So modern supercomputers are in practice, large-scale AI machines. So that's where we are at today. Now, let's talk a little bit about why did this convergence happen also, right? We discussed a little bit about that, but what is the core reason for it? Now, the core reason is scale, right? Because starting around 2018, I'm sure you will definitely remember this because AI models began growing exponentially, right? Now, the time when ChatGPT 1 came out in 2018, the size of the models at roughly around, I don't know, 100 million parameters. I think ChatGPT 1 was around 110 million parameters, right? At that time also, it was already that large and challenging to train, right? Even the 110 or 100 million parameters, right? But very quickly, things sort of accelerated. Within just a few years, model size jumped, several orders of magnitude. As you know, today we are operating at hundreds of billions or even a trillion parameters. The scale is that, right? So examples like ChatGPT 3, I think it's about 170 billion parameters. And even Google has some models with trillions or 1.5 trillion parameter size, parameters as well. So this was not a gradual growth, it was sort of explosive. So the problem is that computer chips did not evolve at the same pace. So if you look at the graph, you can see that there is definitely a compute gap. So Moore's law couldn't continue to deliver the steady incremental improvements in chip performance, but nothing close to the growth rate of compared to the model size, right? So while chips became somewhat faster each year, AI models became dramatically faster. So there was a compute gap there. So as a result, the size of these AI brains or models start increasing nearly 10 times faster. It was not a single chip performance couldn't support that. So it was outgrowing that at that point in time. So the gap between the models required and what individual performance, processors could not deliver with the advancement in chip performance every year. Now, this broke many old assumptions. So for decades, the industry assumed that more powerful chip would always be enough. But we reached a point where a single chip, no matter how advanced, was no longer physically could store and train these models. Now, memory limits, compute limits, electric power limits, right, all were hit at the same time. So that was the sort of wall that we run into. All these issues came at almost the same time, right? And hitting that wall sort of forced the industry to completely rethink how AI systems are built. And instead of relying on faster individual chips, we move towards distributed systems, right? Massive parallelism, and data center scales, architectures, and everything. All these came sort of at the same time. Okay. Yeah. So now we know that there's a compute gap, right? So how do we fix this compute gap? And the answer is something called a scalable intelligence. So in computing, scalability means very simple, right? I'm sure all of you would know if one task sort of takes 100 hours to run on one computer, but if you have 100 computers, then it would take 1 hour, right? It's you add more machines, the work finishes faster. And the idea sounds obvious, but in practice, it's really difficult to achieve. So for a longer time, this kind of scaling was difficult to do, particularly with AI. We'll come to that later. But you could add more computers, but they did not sort of work well together. Like each machine ran its own copy of the workload, but coordination was inefficient. We'll talk about that later in the hardware section. But it was not as simple as adding more computers. So we needed to think out of the box as well. So communication overhead basically grew very quickly, and the performance gains flattened out. So at that point, it did not matter if you add more compute power or chips, but the performance gain was not there, right? So the benefit, cost versus benefit, was not matching. So instead of acting like one system, the machine sort of behaved like isolated systems. Now, this meant that simply adding hardware did not solve the problem, right? So beyond a certain point, more machines just added more complexity and not speed. So this was one of the major barriers of scaling AI models further. There was a lot of discussions within the industry as well, and people were trying different things. and basically scalable intelligence changes that, right? It refers to a modern system architecture where thousands of GPUs are tightly connected and trained to act like a single very large brain. It's different from the HPCs also in some sense, because here the compute, memory, and communication are designed together, so the system behaves as a one coordinated unit. So when we add more hardware in this setup, the AI does not just get bigger; it gets faster and smarter in a very predictable way. So performance improves close to linearly, which is exactly what makes large-scale AI training possible today. I think I have a couple of examples towards the end as well. Okay, so now we have talked about what is the need for such systems or scalable intelligence, why that gradually happened, and what was the turning point in 2018 that we talked about. So we know that there was a compute gap, and we sort of figured out scalable intelligence is the solution. And now we need to talk about the actual hardware that is powering all this. Excuse me, sorry. Sorry. Yeah. So okay. So now let's talk a little bit about the hardware. Okay. So to understand high performance computing, we need to understand the GPU, or more precisely, the difference between CPU and GPU. I know this audience might already covered all this, but I'm gonna quickly give a small example, a simple way to explain in a more business-oriented analogy, maybe. And also a side note, I mean, you might have been hearing a lot about GPUs, especially if you have bought NVIDIA stocks a few years back. You might be so happy, and you know that GPUs are really interesting and also part of the AI revolution as well, right? So, so before that, so think of CPU as a highly skilled specialist. So this person is excellent at complex reasoning, decision making, handling many different types of tasks. They are flexible and intelligent, and they can switch between tasks easily as well. But however, they usually work on one problem at a time, like sequentially, moving step by step in a very precise sequential way. This is exactly how CPUs are designed as well. So, so they have a smaller number of very powerful cores that are optimized for control logic. Now, and branching, and also maybe complex instructions. Okay, so this makes them ideal for operating systems, databases, and general purpose computing. Now, think of GPU as a large operation team on a factory floor. So each worker performs a very simple, repetitive task. Individually, these workers are not solving a complex problem and making decisions. But there are thousands of them, right? So it's not so collectively they're doing all the same operations as well in a highly coordinated way. There is a slightly, I think, similar analogy to AI agents. I'm not sure if you've already covered that topic during the course of these sessions, but how AI agents do that on the application layer, I think it could be an analogy as well in that sense. So. Okay, so this sort of reflects how GPUs are built. They contain thousands of smaller cores designed to execute the same instruction across many pieces of data in parallel. Okay, so GPUs trade flexibility for scale and throughput. So it can do small or same instruction, but across many pieces of data than the traditional CPU method. So AI workloads are not about deep reasoning or at each individual step, right? Instead, they are instead they're about executing millions or billions of very small mathematical operations, especially matrix multiplications. This is important because matrix we have something coming up about matrix multiplications as well. So these operations are simple, but they have to be done at an enormous scale. So the session is all about scale. Right? So if you give this kind of work to a single specialist, even a very smart one, a very capable CPU, it will take far too long. But if you distribute this same across thousands of workers, which is not as sophisticated as a CPU, it completes the works extremely faster. Right? So that's what we need for AI as well. And that is why GPU is also, that is why AI runs on, modern AI runs on GPUs rather than CPUs. And again, that is a time when, if you had bought NVIDIA stocks, it would have been a different story as well. and GPUs are purpose-built for massive parallel execution as well, right? So, which is exactly why today's AI models require to, at scale, to function at scale. Now, I have a small video that demonstrates this. I know it might be, super important, but it's a fun video to watch. I hope I can share the screen and play the video. If you're not hearing the audio, just let me know. Can you see my screen?
Yes. Screen is visible.
One of the engines that does
Yes,
the heavy
audio is
lifting of
also-
this is the GPU. And there's a lot of confusion about what the heck a GPU is and what it does. So they asked us to come here and give a practical demonstration, a kind of a science lesson about how a GPU works. And since the GPU does most of its work in concert with the ultra-important CPU, we thought we'd show you a comparative demonstration. All right, I introduce to you Leonardo. He may look like a skid steer BattleBots platform with a paintball gun mounted on his head, but in fact, at heart, he's a painter. And he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. This paintball gun is an XY servo-driven bot that will readdress itself for each pixel that it has to lay on this canvas right here. 3, 2, 1. Let me speed it up. Oh, you guys are going to love this. Underneath this tarp is thousands of pounds of aluminum and steel, a mile of high-pressure air hose, hundreds of pounds of compressed air, and 1,100 specifically addressed paintballs in 1,100 barrels. Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on this thing, 21, exactly the same length, balls will fly across 7 feet of space. Are you guys ready? The audience is ready, the crew's ready. On your 8,
4, 3, 2, 1.
Ladies and gentlemen.
Okay, so this is sort of a demonstration that NVIDIA did to basically show the difference. I mean, it's super self-explanatory, but I thought it would be a fun video to show. Like we've been discussing, this basically explains the difference between CPU and GPU, or the analogy, right? So now you sort of get an understanding about why the throughput that GPU gives is super important for modern AI, right? Okay, so let me just give me 1 second. Okay, now sorry. Now we've talked about GPUs. Now, even with GPUs, like we discussed in the last slide, the most important parameter or the idea is or the thing that he needs to do is matrix multiplication, right? Now, NVIDIA changed the game with a specific innovation called Tensor Core. Okay. Now, this was not just an incremental improvement; it was a fundamental shift in how hardware sort of supports AI workloads. Now, traditional processors perform math one number at a time, or at best small groups or numbers at once. This approach works well for general purpose computing, like we discussed, but where tasks are diverse and control logic is complex. But however, it's highly inefficient, right, for the type of computation used in modern AI. Now, AI models are built almost entirely on matrix math. Now, instead of working on individual numbers, they operate on large grids of numbers called matrices. Trained on a neural network means performing the same matrix operations, multiplications over and over and again at a massive scale. And I'm assuming you might have already gone through the theory of it already during these sessions. Now, a tensor core is specialized hardware, right, designed specifically for this purpose. And it can multiply entire matrices in a single operations, like we just saw in the analogy of the video as well, rather than processing one value at a time. Right? So this allows GPUs to execute AI workloads orders of magnitude faster than traditional processors. All right. So a useful way to think about it is the difference between using a hand screwdriver and a power drill. Right. Both tools perform the same basic task, but one is purpose built for speed and repeated use. Tensor cores are designed for exactly the kind of repetitive, large-scale math the AI requires, the matrix multiplication. Now, because of this, tensor cores did not just make AI a little faster. It was a fundamental shift. They make large-scale AI feasible in the first place. Even without them, training modern deep learning models would be very slow or expensive or both. Right. So this single innovation is one of the main reasons why the modern deep learning and large-scale AI became practical over the last few years. And I'm sure you've definitely experienced that in your personal life and your professional life as well. And of course, that's the reason why we are actually having this session also in some sense. So it transformed GPUs from graphics processors into true accelerators. And also, speaking of GPUs, there was something else I probably wanted to mention. Like, we've used GPUs for a similar, not so similar, for gaming purposes for a longer period of time, right? But this introduction of the tensor core to the GPU was a fundamental shift that happened when NVIDIA introduced this. Okay, so now, so we've talked about GPU, the tensor core. So speed, raw speed is, we talked about the raw speed or the speed about GPUs, but that's not the only challenge in AI systems, right? So very often the real bottleneck is not computation at all, but memory. Right? So again, to probably give an example, if you have a chef. Right, if you're a chef or if you're a fast chef that can make a lot of food faster, but the ingredients are a few blocks away in the supermarket, it doesn't matter how fast you can make food. You'll probably need to go back and forth and get that from the supermarket, right? So even if the chef is faster, you will not be able to make food faster because you have the dependency. So exactly what happens in AI systems. GPUs are super capable of processing data extremely quickly, as you've seen. But if the data that they need is stored far away, the GPU cannot stay busy. Instead of computing it, it will be like in an idle mode, right? Waiting for data to arrive. So this is usually known as the data bottleneck or memory bottleneck. I'm sure you've heard about this before in different contexts, or the same context as well. But this is a real problem. So as AI models grew larger and faster, this problem becomes more severe, as you would probably imagine. So improvements in compute and no longer translate into the real world performance. Excuse me, because memory couldn't keep up. So in many large scale AI workloads, memory bandwidth, not the compute speed, becomes the limiting factor. So to address this, the modern GPUs use something called as high bandwidth memory, right? So HBMs. Instead of placing memory far away from the motherboards, these are all very practical circumstances or implementations. Like if you ever build a computer or assembled a computer yourself, you can probably imagine in your head how these things would. You would put the CPU somewhere, and then you put the RAM into the slot. The difference between the RAM being on a slot few centimeters away, or maybe on top of it, or embedded into the same CPU, makes a huge difference when we're talking about scale and efficiency and stuff like that. So this is exactly the same issue that we're talking about here as well. So to address this, modern GPUs use HBMs. So HBMs are stacked, memory chips that are stacked next to the CPU or even on top of it, right, as a package, single package. So this dramatically shortens the distance data has to travel. So you can use all the compute power, and the compute mechanism of the GPU does not have to sit idle for a long time as well, right? So you can think of this as putting the fridge next to the chef. So fast chef, fridge is right there. You take the ingredients, you cook something up, and you can get it faster, right? So HBM is expensive and complex to manufacture, and in many ways that's what driving the prices of these GPUs crazy, but also it's very essential for modern AI systems. So without HBM, much of the performance gained from GPUs or tensor core would be wasted, because there's a lot of wait time, right? And large scale AI training will not be efficient as well, right? So okay, so GPU, tensor core, memory, and the next one we're talking about is the connection or the interconnection or the traffic. Okay. So when we scale AI systems to hundreds or even thousands of GPUs, computation is no longer the only challenge, right? At scale, communication becomes just as important as raw compute power. So we've talked about one single instance where a GPU and the HBM is put together. So we have that package. But imagine if we to scale it, because we'll come to that later. But of course, you can already imagine that one single GPU will not be able to process all this what the modern AI requires. So during training, the GPUs must continuously exchange information to stay synchronized. We'll come to that when we talk about the software part of it, why it is necessary as well. But in general, the models are bigger. So one GPU alone will not be able to hold the entirety of the model. So we need to do things like data parallelism or model parallelism to achieve this. So in those instances as well, these GPUs continuously need to exchange information and stay synced. Okay, so this includes sharing model parameters, gradients, or results after every training step. I'm assuming you might have heard a lot about about this in before previous sessions as well. But yeah, so in a very practical sense, also this is why we need that, right? So yeah, so these exchanges happen constantly, not occasionally. So if the communication is slow, the entire system slows down. So in large scale systems, I think, sorry, can you still see my screen? Just confirming. Yeah, just thumbs up. Okay.
Yes, yeah. Yes,
Okay.
yes.
All right. Okay. So in large scale training, GPUs are often GPUs often finish the computation quickly, right, and then wait for the updates from the GPUs. So if the network cannot deliver fast enough data, this is a waste of time. These are I feel like these are simple logic. So standard networking technologies like Ethernet that have been traditionally powering our networking needs for decades was not designed to, for these type of workloads. We're talking about gigabytes, hundreds of gigabytes of data per second, right? So Ethernets work well for general purpose networking, but not for, but it has latency, right? And also bandwidth limits quickly. So there are a lot of bottlenecks if we use the traditional method. So to solve this problem, AI systems use a specialized interconnects such as NVLink and InfiniBand. These are the interconnects that help us mitigate this traffic problem. So these technologies are built specifically for high throughput, right? Low latency, high throughput and low latency communication. So they allow the GPUs to exchange data in an extremely high speed and often bypassing the CPU entirely. So with these interconnects, GPUs can communicate almost as if they were part of a single machine, right? So even if we are physically placing these GPUs next to each other, or I don't know, apart from each other, now because of NVLinks and InfiniBands or these specialized interconnects, it will virtually act as a single system to some extent. Okay. So in modern AI clusters, interconnect speeds can reach, like I said, hundreds of gigabytes per second actually. And without this level of communication performance, large-scale AI would not be practical, no matter how powerful the GPU is. So this is also a very important aspect of the hardware package that we're talking about. Okay, so sorry. The GPUs, TensorFlows, HBMs, interconnects. What do we get if we put all these together? So the moment we put all these together, when we combine everything that we discussed so far, the GPUs, the HBMs, the high-speed interconnects, we arrive at something that's called as a superpod. It looks like a traditional server rack, but this is where individual components become a complete AI system. So a superpod is a tightly integrated system, right? Usually delivers one or more server racks. Physically, it may be about the size of a fridge or a refrigerator, but functionally it behaves like a single supercomputer. That's very important, right? So from a software point of view, it's treated as a one large coherent machine rather than separate servers. Okay, so instead of superpod, GPUs are connected using technologies, like I said, like NVLink and high-speed networking, the compute, memory, access, and communication are all designed together to work as a single system. So this tight integration is what allows the system to avoid many of the bottlenecks that we discussed earlier. Now, because communication is fast and predictable, large AI models can be trained efficiently across many GPUs, and the system scales in a controlled way, rather than becoming slower or unstable as more hardware is added. So modern AI data centers are built by deploying many of these superpods. I think I have a couple of examples coming up, and also on Funny Code by Sam Altman as well. So by connecting them together at a higher level, so this modular approach, it's as simple as, I don't know if I want to simplify it like that, but still, it's as simple as putting two fridges together to increase the compute capacity and power and everything for training your AI models. So yeah, so for this reason, the superpod has become the fundamental building block of large-scale AI infrastructure. Right? It's basically represents the practical unit of scale for modern AI systems. Okay. Before we move on to the software part, I have a question to ask. So can we go back to our menti.com? Second. Yeah. all of you and me can take a break, and we have 30 seconds to 1 minute. This is anonymous, just for a fun. What do you think the hardware cost of a single NVIDIA SuperPod would be? I don't know, I can see 150 people here. Come on. Okay. I can see 18 people here. So I'll just wait for those 18 of you guys to finish putting in your poll. Okay, 20 seconds more. Okay, so I think the majority of the people think it's close to 5 million USD. Okay, so in reality, it's actually 10 to 15 million USD. So 100, give and take 100 crores for one SuperPod. So it's crazy expensive. And I'm sure you've probably heard a lot, about the investments that these AI companies are getting, or the infrastructure building, commitments that these NVIDIAs and others are giving to the governments and everything. The investments that they would love to do are in billions of dollars, right? Hundreds of billions of dollars, because it is expensive. And I think this cost only talks about the hardware, the server rack, or the hardware cost, but actually running these data centers are more costlier. I think we have a slide about that, a small slide, but you can imagine, right? So it requires a lot of power, massive infrastructure, a lot of power. And of course, if all of these things are, running together, and you can, if you've ever played video games using GPUs, you know that how hot or, hot it can get. So you need massive cooling facilities as well. So yeah, but these things are really, really, really expensive, what we're talking about. Okay, so let's go back to our slides. So now, until now, we've talked about the hardware systems that we need to power, our AI endeavors. But as you could imagine, without good software controlling whatever we talked about, the memory management, the data transfer, the synchronization, we need really good software also to power or to complement the hardware that we've just described. So basically, the next question is how we actually run AI software on top of all this infrastructure. Now we have SuperPods, consisting of small GPUs with high bandwidth memory in it, and the infilling and the other sophisticated networking between. So we have the hardware or the infrastructure there. Now, having powerful hardware alone is not enough, right? Because we need a way to use it effectively. And modern AIs are extremely large, like modern models like GPT-4, for example, hundreds of gigabytes in size when fully loaded into memory. In contrast, a single CPU, sorry, a single GPU, even a very high-end one, typically has around 80 GB or 80 GB of memory. Simply put, they will not be able to run the entire model of GPU, no matter how powerful it is, right? So because of this limitation, we are forced to split the model across many GPUs. And we will talk about that strategy later. This is where like different parts of the model live on different devices, and each GPU is responsible for only a portion of the overall computation. So these GPUs must often work together as a part of a single training process, and this approach is called distributed training, right? Why do we need to do that? Because it's, models are large. We can't, one GPU cannot handle it, so we basically have to split it. Then because of this, we need to have a strategy called distributed training to enable that. So distributed training is not just about splitting memory or dividing of storage. It is a much deeper challenge as well. So the GPUs must consistently coordinate with each other, right? Exchange immediate results and stay synchronized at every single step. So this communication happens continuously and at a very high speed. Yeah, I think I have one example maybe in the next slide. So if coordination of this is not handled correctly, right, the synchronization, because imagine we started training and then the model is distributed, and then there is a sync issue or a synchronization issue. The whole training is corrupted. So you have to start again. So it's super important to have really good hardware. At the same time, it's super important to have really good software and fallback systems in place so that we can do these trainings and more model training and everything effectively and successfully. Right? So if coordination is not handled correctly, the performance drops, and it can entirely fail as well, mainly because of synchronization. So this is where the software architecture becomes just as or more important as the hardware capability as well. Okay. Yeah. So the first and the simplest strategy for distributed training is called data parallelism. So just want to get an idea, have we talked about this in previous sessions, data parallelism or model parallelism? Thumbs up, thumbs down. No? Oh, okay. Okay. I'll quickly glance through it in any case. Just wanted to get an idea. So the simplest strategy for distributed training is this, the data parallelism, right? So in data parallelism, every GPU holds an identical copy of the model. This is possible if the model is small enough to be loaded into a single GPU. Just keep that in mind. So the structure and parameters of the model are same on each devices. What changes is the data, right? The GPU receives a different subset of training data and process that data independently, right? And all GPUs run the same computation at the same time, right? But on different data batches. Now this allows training to scale effectively because because the work is evenly distributed across devices. And after each training step, the results are sort of synchronized. Most commonly, the gradients they computed are synchronized, right? They share it within the GPUs. And then these gradients are then aggregated and then used to update the model parameters. Once this update is completed, all GPUs synchronize. So they again hold the identical copy of the model. So that's how step by step the process happens, and this synchronization step is very critical because it ensures that all the GPUs continue learning from the same model state. Otherwise, it will be corrupted or will not get the result that we anticipate. So this approach is relatively easy to implement compared to other distributed strategies, as you would imagine, as it scales well across many GPUs. Because of the simplicity and effectiveness, data parallelism is actually used in majority of large-scale AI training systems today, and sort of forms the backbone of many production AI workflows as well. Okay. All right. So the quickly again, the second strategy, I think you're already discussed about this. It's model parallelism. Sorry. So data parallelism works well when the model fits in a. Sorry. Oh, sorry. I think somebody wants to join the call. I got distracted. Sorry.
Yes, sir. If someone wants to join the meeting.
So I thought my connection dropped. So yeah. So as I was saying, data parallelism works if the model fits in a single GPU, right? And as long as the GPU can store the full model, this approach is simple and effective. But very large models, for the large models, that assumption does not hold, right? So the model itself becomes too large to fit into the memory of one GPU. In this situation, we turn into model parallelism. So instead of copying the full model in every GPU, we split the model across multiple GPUs, right? So one GPU holds the first layer and the next holds the following layers and so on. And each GPU is responsible for only the portion of the neural network. Now, during training, data flows from this end to that end, so through the model step by step. And this starts on the first GPU where initial layers are computed. The determined results are then passed to the second GPU, and then which processes the next set of layers. And this continues until the data has passed through the entire model. And then each GPU only computes is the section that is assigned to that particular network. This approach allows us to train models that are far larger than the memory capacity of a single GPU. Without model parallelism, today's large models simply could not exist. I'm sure you would know that. However, this approach introduces new challenges, right? So because, if you imagine this particular flow, so GPU is dependent on each other in sequence. So coordination becomes more complex. Communication between GPUs must be fast and reliable. Delays can reduce performance. But despite this added complexity, model parallelism is essential for training large AI models today. So it represents a necessary trade-off, right, between complexity and the ability to scale. Okay, so we've talked about first strategy, data parallelism, where the model can fit in a GPU. And then the second one is model parallelism, where the model will not be able to basically fit into a GPU. We split it up. I'll quickly go to the next one. I think we're running a bit low on time. Okay, so we talked about model parallelism, and we know that it allows us to split very large models across multiple GPUs, right? But this also introduces a new problem. I'm sure you might have thought about it already, but because different GPUs handle different parts of the model, some GPU may finish work early, and then it will be waiting for the next still processing. When this happens, parts of the system still idle, right? We don't want that, because we want to use the available compute power when it is available without delay, so that because one of the most valuable asset is compute capacity, and we cannot waste that, right? So pipeline parallelism is designed specifically to reduce the idle time. Instead of waiting for one data batch to fully pass through the entire model, so before starting the next one, we allow multiple data batches to move through the system. It's a very simple process to probably visualize. And when we get deeper into it, it has complex elements to it, but I think it's easy to imagine, right? So this approach keeps GPUs active for most of the training processes. Rather than stopping and waiting, the system maintains a steady flow. Much like an assembly pipeline where different stages are working in parallel, right? So that's what's happening here. You get a much higher overall efficiency when you do this, and pipeline parallelism can significantly speed up large model training by making better use of the available hardware compute as well, right? But it also increases the software complexity. Excuse me. I'm sure you'll be able to imagine this as well, because just the synchronization can be a lot, but if you have multiple things to synchronize at the same time, the complexity is again multi-fold. Scheduling, synchronization, memory management become a lot more challenging. So yeah, so we've talked about 3 strategies, or two strategies: data parallelism, model parallelism, and pipeline parallelism as well. I'll quickly just go through the software stack as well. I don't know how important this is right now, but again, everything we discussed so far sounds complex to implement, right? That is because it truly is complex, but also writing all this logic from scratch would be really difficult, and nobody wants to do that. Can be time consuming, it can be error prone. So even small mistakes in synchronization can cause the training to fail, right? So the key point is that most researchers or engineers do not write this low-level code. Instead, they rely on specialized software libraries like DeepMind from Microsoft. I think it's from Microsoft. Yes. Sorry. Yeah. Sorry. DeepMind and Megatron, and then these are often built on top of frameworks. I'm sure you've heard about PyTorch or TensorFlow. So these libraries handle the hardest part of distributed training. They decide how to split the model across GPUs, how to split the schedule of data, or split and schedule the data, and then how to manage communication between devices and how to keep all these GPUs synchronized throughout training. Now, they also handle memory optimization and performance tuning and fault tolerance, things like that. Right? So from a user perspective, much of this complexity is hidden. As a user, you define the model architecture, specify the available hardware, 8 GPUs, 100 GPUs, 1,000 GPUs, and based on that information, the software stack automatically determines the most efficient way to, run the training job. This abstraction is critical, but right. So, sorry, this abstraction is critical. It allows researchers or students to focus on model design and explanation rather than low-level system engineering. So, just an FYI at this point, I guess. In this sense, the software stack is what turns the powerful, complex hardware into something practical and scalable and ready for real-world AI deployment or AI development. So we have the hardware, the CUDA cores, or the Nickels, and then DeepSeek, Megatron. And so this is sort of an enterprise AI technology stack would look like. I don't think any of us would really will be working on this. Yeah, but if you want to spin up something and do some AI training, I think there are other options from Google, Colab and everything that you can do. I've slightly mentioned it in the next slide, so we can discuss it there. Okay, so everything we've discussed so far mainly applies to training. Like we've talked about training models and everything. Training is the process of teaching the AI model. It involves processing massive data sets, updating billions or even trillions of parameters, and running continuously for weeks or sometimes months, right? This typically requires thousands of GPUs working together, as we discussed so far. So training is extremely compute intensive, as you can see on the left. Sorry. 1 second. Sorry about that. Yeah. So the goal. So training is extremely compute intensive. The goal is to maximize the throughput so the model can learn as efficiently as possible. During this phase, speed and scale matter more than responsiveness, right? And small delays are usually acceptable as long as the process continues. Now, once training is complete, the model is fixed, right? And at that point, we move to inference. Inference is simply using the trained model to generate outputs, right? So here, like answering questions or text or classifying images or whatever that may be, whatever you potentially do the application layer using ChatGPT or Gemini. So no learning happens during inference. The model weights sort of stay the same. Now inference requires much less compute per request compared to training. However, if you really think about it, inference introduces a different challenge, right? Like instead of running a one large job, the system must serve many users at the same time. So it brings back the same complexity. So when you are training the model, you have large data sets. There's a lot of complexity there. During inference, it's not just one parameter. The parameter is probably very small. The input is very small, but you're looking at millions or billions of inputs at the same time. So even though it's not given at the same time, but when small instructions are given at the same time, then the complexity again becomes bigger. So inference requires much less compute compared to training. However, the inference introduces a different challenge here. Like instead of running one large job, many users at the same time. So the response has to be quick. So latency becomes critical here, and even small delays are not visible to users. So in real world, you can probably imagine once you send a query to ChatGPT, it takes a lot of time to get back. You see that. So the response time is important there. So because of this scale and latency requirement, inference still relies on the large high-performance HPCs as well. So these systems are optimized differently from training clusters. Hardware could be same, but it is optimized in a different way, often focusing on efficiency, batching, fast response times, right? So while training and inference often use similar hardware, they're optimized for different goals. Training focus on raw compute data, so compute throughput and long-running jobs. Inference focus on speed, efficiency, scalability to million people, a million requests at the same time. So that's the difference between inference and training, how it is using the same sort of hardware, and why the same HPCs are required for both. And what are the differences? Okay, so real world examples. I'll just quickly go through it. 50 minutes, okay. Sorry. So I'm sure you've all heard about GPT. Right now it's GPT 5.2, I guess. But for GPT 4, right? These models show that what happens when AI is pushed to the extreme limits. And I'm sure you're all seeing that effect in your personal and professional life. So GPT-4 was trained using roughly, 25,000 NVIDIA chips, which is A100 GPUs for several months, 5, 6, 8 months. At this scale, the primary challenge is no longer like raw computation. Right? Compute is important, but the dominant challenge becomes reliability and system stability. So when you operate tens and thousands of GPUs at the same time, the hardware failure are not a rare event. You can imagine, right? 1,000 GPUs running together, doing the same thing, it will fail. Right? So they are expected every day something will fail. So a GPU may stop responding, a network link may, drop a few packets here and there, an entire server may go offline. So this is simply the reality of operating this at scale. And because of this, the training systems must be designed to expect failure as well. So continuous monitoring of health of hardware and detect programs automatically. And when failure occurs, the system sort of needs to pause the training safely, then isolate the faulty component, reassign the workload or change that component, and then, resume training. The important thing is that it has to be automatic, right? So all of this must happen without losing any progress. Losing model state of training history would means, so you might be, running it through for weeks. So if you lose a state or during this process, if you're not able to save the state and continue after detecting a fault, it's weeks of training data or everything lost. So this is what makes training large language models, a large scale distributed systems problem. So not just machine learning problem. So the successful completion depends on many factors, right? So fault tolerance, orchestration, recovery, algorithms, everything. So it's not a simple, easy task, but we have software solutions or systems in place to do that to a lot of extent, but still it requires a lot of care and clarity. Okay, so another case study is AI for science. When we talk about AI, most of the people will, not this group, but most of the people will be thinking about chatbots or Gemini or ChatGPT. But some of the most impactful uses of AI are happening in the scientific research, right? So I don't know if you guys have heard about AlphaFold. So using these high perform HPCs, AlphaFold was able to predict the structure of nearly every protein that's known. So protein folding is an extremely complex problem. So doing this experiment and for us to do it manually, it would have taken unrealistic amount of time, maybe centuries. But combing AI models with massive compute, AlphaFold sort of compressed decades of scientific work into a short period, right? And another important example is climate modeling. Researchers are sort of building a digital twin of the world right now, and you can imagine the amount of data and the compute that is needed for that. These systems combine traditional physics-based simulations with AI models trained on large data sets. The goal is to better understand, complex climate dynamics and improve accuracy of prediction, right? So so these big breakthroughs are only possible because of scalable intelligence is what is the point that I'm trying to make. They require massive compute resources, enormous data sets, and advanced distributed systems working together as well. So these are large, important problems that are being solved today. It clearly shows that AI infrastructure is no longer a technology product. It becomes a core scientific tool, and similar importance to, particle accelerators or supercomputers or earlier as well. So and finally, we're coming towards the end. I just wanted to brush up on this topic as well. So when we talk about HPCs or modern AI, this is one of the topics that usually tag along, that tags along. So the level of AI performance that we're talking about comes at a real cost, right? The energy required to train these AI models is super significant, and it cannot be ignored, right? So training a single large model can consume enough electricity to the carbon emission of multiple cars over their entire lifetime. That's the scale that we are possibly looking at. So when models grow larger, the training lasts longer, energy consumptions scales quickly. There's no longer a marginal issue. It becomes one of the dominant constraints on how fast AI can grow, right? So modern AI data centers can operate at a scale of megawatts. We're talking about, I have a poll for you, so maybe I'll just reserve that for later. But power consumption, cooling requirement, carbon emissions, these are all major concerns. and not side issues. So in many cases, cooling alone accounts for a large fraction of total energy use. Like I said, these things produce heat, a lot of heat. So this basically raises a lot of important ethical, questions as well. So, as a result of all this, we are moving towards something called as green AI. The goal of green AI is not to slow down the process per se, but to reduce the energy usage, right? So this includes designing more efficient hardware, improving the software, and reducing waste and everything. And another important approach is smarter infrastructure design. Things like putting your data centers in colder regions, right? So if we were to build one in Kerala, maybe just not put it in Palakkad and probably put it in Munnar. I don't know. Those kind of decisions. So because it will require less energy to cool. The cooling, like I said, is one of the most important factors. And so sustainability is no longer just an optional consideration. It's becoming one of the more constraints when you think about AI. But there are other, there's no way going back. There's no way we will not have AI or stop. We will not be able to stop it. So that's not the idea as well. It's about more conscious designs and conscious choices that we'll make in the future, probably. Okay. So one final thing before we sort of close the session. So we've talked about, so the future of AI is not about building bigger and bigger models. Scale has driven much of the recent progress, sure, but it's no longer the only direction forward. Okay, increasing the focus is also making the models more efficient, and that's one of the key aspects of becoming green AI as well. So one important technique enabled this shift is called quantization. So traditionally, AI models use 16-bit or 32-bit numbers to represent values during computation. Right? This level of numerical precision comes from the scientific community, but research has shown that it is often not needed or unnecessary for AI workloads. So many models continue to perform extremely well using much lower precision. So in practice, many modern models can run in 8-bit or 4-bit even 4-bit arithmetic while losing very little accuracy. So that's the trade-off, right? So if you're getting the similar or good results, even comparing 3216 or 4-bit arithmetic, then why use the other one? So that's the consideration. Then one of the analysis is taking the video from 4K to 180, 1080p, HD and 4K. The difference is not that visible on a small screen, at least. So to most users, there is no difference, is what I'm trying to say. So we can use 4-bit arithmetic to get good results, right? So the quantization reduces memory usage, lower energy consumption, and speed up inference as well. So this also reduces the pressure on the memory bandwidth, right? So allow models to fit in a small hardware footprints as well. So because of this, because of quantization, makes it possible for us to run powerful AI models on smaller systems as well, including maybe laptops or edge devices, right? Even on mobile phones. I'm sure that's going to be the future. But yeah, as a result, efficiency will be just as important as slow scale in the next phase of AI development. Sort of deciding where and how AI can be deployed, right? Okay, so conclusion, I'm not going to go detail into this, but as a faculty, how can you start or how can you guide your, I don't know, probably you might have already discussed this in your sessions, but these are some. So we've talked about huge infrastructure and everything, but it's not like you can't try out training models or anything. There are already platforms, free and low cost, and it's more powerful enough for teaching or experimentation. So you can probably take note of some of these tools. I'm sure there are free tiers for all of this to sort of spin up, a small training, try out training a small model or things like that. You can do that. So AWS, sure, all these offer student packages as well if you want to try out yourself on how to train a model or something. I just wanted to fit it into the presentation. It's not, super important, but yeah. So to wrap up, there are 5 key points, right? 4 points, the ideas. It's first, AI has clearly moved beyond individual machines. Modern AI systems no longer live in laptops. We already discussed that. They live in data centers. Scale is no longer optional. It's fundamental requirement for modern AI. And the second is scale requires specialized hardware, like we said, GPUs, HBMs, tensor cores, faster interconnects, all these things. So these are core requirements. The third, hardware is not enough. It requires specialized software, specialized strategies as well. And then, taken together, this is the combination of hardware and software is actually powering the modern scalable intelligence as we see today. And sort of a summary slide. I think I think we have 5 more minutes. But I think I'll quickly, this is just wrapping up, everything in one sort of slide. I'll stop now. And this is basically me, if you would like to reach me. I think the presentation, if you're interested, will be shared among the participants, is my understanding, or I can send it to you as well. Mail is there. If you want to connect me through socials, the QR scan is also there. One thing that I would like to mention before I close the session is the practical. One practical thing I did. The entire presentation was actually built using AI. So, all these illustrations that you see are single short prompt images, all of them. So I just wanted to mention that because we are seeing the impact of AI in real world as well. But yeah, so thank you again. I think we have 2 more minutes, but thanks a lot for this opportunity to be able to share this with you. If there are any questions, I'll be happy to answer over emails. I think we are. But again, thank you so much for this opportunity. I had one more poll, but I'm not going to run that. Thank you so much.
So thank you, Jibin, for that wonderful session. Participants, if you have any queries, you can either type in the chat box or you can directly ask the resource person. So Jibin, to ask about like the processes that you do inside, right? So is it impacted, what is the impact of AI you feel in your day-to-day activities, or what CIED does?
Sorry, what was the last?
No, with regard to what CIED does, the kind of processes, what is the impact of AI in the business process, that kind of activities?
So you're asking about the impact of AI in my organization, right?
Yes.
What we do. Okay, so I think with regards to what we do in CIED, I'll give you a perspective of how the B2B companies are thinking about it. Okay, so we've been working on the AI product for the last 4 years or 3.5 years. So in the last 2 years, everyone was like thinking about AI. Oh, we don't know if there is clear ROI, things like that. But right now, we are a solution provider. We are building AI agents to automate supply chain workflows for companies. What we have seen is that a lot of these companies are now beginning to fast track implementation of AI within their operations. And we've seen that in the last 6 months, it has accelerated as well. So for us as a company, we are really struggling to keep up with the pace. There are multi-pronged. One is the requirement from the customers, and the other one, the AI advancements as well. So I'll give you a simple example, right? In our product, there are different pipelines through which we achieve this operational efficiency. So we're building different things using the assumption that AI can do this today and may be able to do it in the future. Now, in 3 months, we are getting a new model which does some of these things that we thought will not be possible in a year or more. And in 3 months, we already have that. So we have to rewrite a lot of these internal workflows ourselves to cater to the demand or the progress as well. Otherwise, our competitors will win. So on one side, it's really interesting that we have a lot of interest from our customers. We are struggling to keep up with that. On the other side, within our product development cycle also, it's sort of impacting, because once you write code and once you have that workflow and everything, in 3 months, we could actually make it 3x efficient. So we should be doing that as well. So the impact is real. In my personal life, like I said, including creating this PPT, AI is doing that for me. And the research and the Q&A research and everything that would have taken, I don't know, 2-3 days, it's coming down to 3 hours or 4 hours of my time. So that's the personal impact. And of course, I don't write my own emails these days. AI does that for me. And of course, the scheduling is done by AI. And of course, I'm a salesperson. I'm a business development and salesperson. Finding out prospects, preparing their profiles and sending out emails to them, everything is done by AI these days. So real impact, yes.
Thank you. And one more question: how might future trend like agentic AI change high performance computing and its role in achieving next gen intelligence? It's a question in the chat.
Sorry.
Impact of agentic AI in HPC and
Yeah. So it's already here, right? Agentic AI is not the future. I think it's the present. So with regards to HPC, if you compare HPC, if you sort of think about all these new advancements that are coming, we definitely have an impact or need for more high performance computing and data structures and everything. But I think in future, the goal is going to be not just simply adding more hardware or adding more compute, but rather how can we make what we have more efficient in some sense. So I'm not specifically mentioning about agentic AI or any advancements that are coming up, right? So how can we make more efficiency or do more without actually increasing the compute power or power requirements by optimizing algorithms or optimizing workflows or optimizing the software that actually runs these HPCs as well. I think a lot of these conversations will happen in the future for the future. It's already there. It's already happening there. And of course, when we are gearing towards AGI, I don't know how that's going, when that's going, or if that has happened already. But when we have that, it's going to be a different ball game altogether.
So thank you. I think if there are no more questions, coordinators, we can start with the acknowledging session.
On
Thank
behalf
you.
of On behalf of Department of Computer Science and Engineering at TocH Institute of Science and Technology, we extend our sincere gratitude for your exceptional session during our AICTE ATAL sponsored faculty development program. Your expertise provided invaluable clarity on the intersection of HPC and modern AI. The discussion on the reason behind the advancement of AI through scaling was particularly illuminating. The detailed comparison of CPU versus GPU differences, complete with examples, helped solidify complex hardware concepts for all participants. Furthermore, your insights into specialized hardware like the tensor core and the identification of memory as a hidden bottleneck and the traffic problem were highly relevant to current challenges in the field. The overview of the super POD architecture and the challenges inherent in distributed training provided a comprehensive look at the future of scalable intelligence. Your contribution significantly enhanced the FDP experience. Thank you once again for your time and expertise. Thank you, sir.
Hey, thank you so much. Really enjoyed the session. Thank you so much, and appreciate the opportunity as
For
well.
the participants over here and for the organizing committee, we would like to present our token of appreciation in the form of a virtual memento. Kindly accept it, sir.
Thank you. It looks wonderful. Thank you.
Thank you, sir.
Thanks a lot. Have a good one. Bye-bye.
So thank you. Thank you so much, Jibin, for joining.
Sure, man. Thank you. Bye.
Bye.